Welcome. My name is John Milbury, and I am honored to be with you today. During our session, I promise to increase your awareness and understanding of how Delmia-NC programming applications relate to the many CAD products offered by Dassault Systems. In so many words, the question becomes, how does a Delmia-NC application, like shop floor machining, make use of file types such as STEP, Solidworks, Catia, xDesign, and xShape? As you may be aware, the Delmia-NC applications themselves have no ability to create design geometry. Rather, they rely on CAD systems to supply the design model to be machined. It is therefore important to understand how Delmia-NC handshakes with our CAD systems and the workflows involved. In order to create NC toolpaths, Delmia-NC applications require a physical product object that contains a 3D shape object. Think of this simply as a 3D part. The 3D part contains planes, ordered geometric sets, reference elements, solid bodies, and other objects related to solid models and their topology. Once a 3D part is chosen for machining, the next step is to load or mount the part into a predefined manufacturing cell. The Mount and Import Resources command is used to accomplish this task. When mounting a 3D part, the new manufacturing product container is created and added to our manufacturing cell. The manufacturing product contains our 3D part to be machined and acts as a container for additional resources needed to create toolpaths. Let's review and discuss the details of a workflow for importing a step file onto the platform and then adding the resulting 3D part into our shop floor machining application. As you can see, we have an existing PPR context, a manufacturing cell, and a kinematic digital twin of our Tormach 770 milling machine. Let's hide our machine for the time being, and then utilizing the plus sign in the upper right corner, we can choose Import. And then select the file to import. After completion, an operation result is displayed along with the full path location for a detailed operation report. Next, we select our PPR Context tab containing our machining cell and select the Mount and Import Resources command. There are many different types of resources we can mount or import, such as tools, stock, rotary devices, and in this case, our 3D part, which is chosen by selecting the tab and then the top node of the 3D parts tree display. The focus is then automatically shifted back to our PPR context, and the 3D part is now displayed in the tree and graphics area. A new manufacturing product was created and added to our manufacturing cell. This manufacturing product contains our 3D part to be machined. Let's access the shop floor machining wizard to guide us in defining our rough stock. We will use the default calculated bounding box without offset values for the size of our rough stock. Okay, now that we understand the basic workflow, let's import a Solidworks part that contains multiple bodies as a result from a tooling split feature. After importation is complete, the ordered geometrical set of the 3D shape has the same multiple bodies as our Solidworks part. We're only interested in machining the cavity body, so we can choose to hide the extra bodies, or we can edit the 3D shape in Catia part design, Editing allows us to delete the 4 unwanted bodies. And double-clicking the top node puts us back into the shop floor machining app. So jumping in and out of Catia part design is quick and easy when the need arises to make changes or add additional info to a 3D part, such as a plane or coordinate system. So the next step is to bring this 3D part into our manufacturing cell for toolpath creation. Let's use the same mount and import resources workflow that we used earlier. Once again, we can select our 3D part tab, the top node in the tree, and the 3D part is now automatically placed in a new manufacturing product within our manufacturing cell. Next, we could invoke the machining wizard, define the stock, and then create our toolpaths. Okay, next let's take a look at xDesign, an app that runs in our web browser and allows us to make 3D parametric solid models. In this example, we begin by importing a Catia part file into our xDesign session. Let's add additional features by selecting a face to sketch on, and then sketching a circle. We can extrude the sketch circle to create a cut feature with an end effect that is through all in both directions. Our xDesign part is now a combination of an imported Catia file along with this additional parametric cut feature. So let's save our design. Let's switch to our shop floor machining application and search for our new xDesign 3D part. After locating our part, we can use Open Advanced to open the physical product in our machining application. Turning our focus back to the PPR context with our manufacturing cell, we can use our mount and import resources workflow to once again create a manufacturing product within our manufacturing cell that contains our 3D part for machining. Let's import another Solidworks part, but this time let's take advantage of the Solidworks configurations that are present in the model. The import dialog box now contains a drop-down that lists the 3 configurations present in the model. We have the forging die, the valve body forging, and finally both the forging and the die. Let's select our forging die configuration. After importation, just the body for the forging die appears in the ordered geometrical set. The 3D Experience platform understands and leverages SOLIDWORKS configurations, thereby streamlining our import process. So let's go back to our PPR containing our Tormach manufacturing cell. Unfortunately, our forging die is too large for this machine. Instead, let's use our Haas VF2. The Haas has the travel limits and clearance we need to get this job done. Going back to our die, we need to create a coordinate system, so later we can accurately position the die into our Haas machine. A simple double click, and we can use Catia part design to create our axis system. Our axis system can be located and oriented anywhere on our part. And after creation, it appears in the tree. Let's go back to our Haas machine and use the now familiar mount and import resources workflow. Selecting our die and its upper level tree node, the part is brought into our manufacturing cell, and we are prompted to select the axis we created moments ago. Now, once selected, our machine appears, and we can mount the part to a pre-existing axis system on the machine table. After initial placement, the robot allows us to translate and rotate the forging die to any location we choose. So let's hide our machine while we program this part. Using the shop floor machining wizard as a guide, we can create our raw stock as a new part that utilizes the extents of the part to be machined. Next, we create a part operation, which allows us to identify the rough stock, select the design part to be machined, create a safety plane a specified distance above the part for tool clearance, and finally define a work coordinate system that will be the XYZ0 for our G-code. Now we can dismiss our wizard and turn our attention to the activities process tree where toolpaths are documented as NC processes. We begin by selecting our part operation and creating a manufacturing program. Next, we specify our machining operations. So let's use a rough surface machining operation to do our initial rough out of the material. We can choose, a 3/4 inch flat end mill. I'm going to select the default tool axis vector of 001 and then select the entire part for roughing. Next, let's specify a 0.5 millimeter as the stock to be left on the finished part. And then let's calculate our tool path. There are many machining options available for the roughing operation, but we have chosen to use almost all the default options for this example. Now in the simulation, I can control the speed, the color, and I can detect tool and part collisions while verifying my tool path. So everything looks great. So let's move on to our semi-finishing operation. So we're going to use a sweeping operation to semi-finish our part. Once again, we choose the part for our sweeping tool path. Let's choose a different tool, however, for this operation. Now, a 3/8 inch extended ball mill will effectively machine deep into the valleys of the die. A zigzag strategy of both climb and conventional milling is chosen, and we will use the default constant step over mode with a user specified distance of 1¼ millimeter. So let's calculate our tool path. And after our tool path appears, the intermediate stock is automatically calculated and then displayed for the start of our simulation. So let's simulate, and we can see our zigzag strategy in action. Notice that with a constant step over, the steep near vertical wall seems to have some large pieces of leftover material called cusps. Let's see if this happens again on the approaching near vertical wall. Yep, it sure did. So I guess sometimes we can't always get away with using the default machining options. In this case, we can specify the height or amount of our leftover material by choosing a dynamic step-over mode called scallop height. By specifying a small scallop height, the sweeping operation will detect the near vertical wall topology and then tighten the step-over amount in order to meet the specified scallop height. Now we can see we are getting some very smooth vertical walls using this new machining strategy. But what about machine tool simulation? Showing just toolpath simulation does not help me to understand if I've crashed the tool into the machine somewhere. In other words, we can view the NC machine moving during the toolpath simulation. Now, this type of simulation can visually and programmatically reveal that the toolpaths are free of any type of stock or machine collisions. This is going to save you time and money while promoting shop safety. Next, let's take a look at xShape, our subdivision modeling tool that runs in our web browser on the 3D Experience platform. Now, xShape is used for creating industrial designs that utilize organic shapes with very, very smooth transitions. So let's select our Collaborative Spaces tab and then simply right mouse button over our xShape part. We can now specify an application, and our 3D part opens as a physical product that contains our 3D shape object. We can now set our focus to our PPR context containing our manufacturing cell, and once again use our mount and import resources workflow. Once again, this workflow creates a manufacturing product within our manufacturing cell that contains our 3D part for machining. So what about Catia files? Earlier you watched me import them into a xDesign part, but how do I get native CAD parts and CAD products onto the 3D Experience platform? Well, the answer can be found just to the right of the import command pull-down, Catia files. So let's open a helical cutter CAD part, and using the defaults, let's import the file into the 3D Experience platform. Let's dismiss the import message and make note that we are in the Catia part design application. As such, we have full control of our model, such as changing the color, viewing the feature tree, and even making parametric changes to the model. Setting the focus on our PPR context contains our manufacturing cell. We can once again use the mounted import resources workflow to bring the Catia part into our shop floor machining app. Let's shift our focus to the Solidworks Connector for the 3D Experience platform. The connector can store and manage SOLIDWORKS documents on the 3D Experience platform. The connector is directly integrated into SOLIDWORKS, delivering just the right amount of data management functionality in a simple and familiar interface. Once on the cloud, the desktop data may be automatically converted and leveraged by any 3D Experience platform application. Now here's a great example of a simple workflow for SOLIDWORKS into the shop floor machining app using the connector. We begin with disassembly and the need to create toolpaths for the base casting of this compound sine table. Let's open the machine casting in its own window and add in the 3D Experience connector. The connector uses the familiar SOLIDWORKS task pane to interface with the user. After logging into the platform, users may choose the collaborative space for their SOLIDWORKS files. A simple right mouse button on the file allows the user to save the document with options. In this case, the Convert checkbox is selected so that we may open the casting in shop floor machining. Also, a bookmark folder can be specified, and in this example, it's a folder named Parts to Program. And finally, a revision comment may be entered. This part is then uploaded to the 3D Experience Cloud. Now, shifting our focus to the shop floor machining app, we can go to our bookmarks folder and locate the part. We can open the part and see that it resides as a physical product with a 3D shape object. This is our 3D part, and we can now use the Mount and Import Resources workflow to bring this into our manufacturing cell for NC programming. One last, very important thing I must mention before I go. Please take a moment to visit and interact with your Delmia fabrication community, where users, resellers, and DS employees go to discuss and collaborate on the latest news about Delmia fabrication products. So I hope you have enjoyed this presentation, and I hope I was able to keep my promise of increasing your awareness and understanding of how Delmia-NC programming applications relate to the many CAD products offered by Dassault Systems. Thank you, and I hope to see you soon.